Ta-da. So, hello everyone. My name is Dmitri Goloubentsev, and I've been a quant for a number of years. Not that long time ago, I started a new company called MatLogica, and this was about building a tool I wanted to have as a quant. And I worked at various institutions. I worked at Canadian Bank, UK banks, and my latest projects were quite computationally demanding. It was about MVA risk calculations, and that resulted in me building this new way of implementing algorithmic differentiation. So I'm going to go and first talk about the agenda we're going to do today. So I first want to speak a little bit about what I really want to have in a quant library, and what do you think? Right. Sorry, my video was out. I'm back in, and you can now see me, I guess. So I want to first speak about what do you want to see in a quant library, and what I wanted to see in the quant library, and how MatLogica can help to address these needs. And then I will turn into practical implementation. Me myself being a quant, I didn't want something theoretical. I wanted to something I can use in practice and something I can use in very large code bases. I'm going to do a live demo. So we did apply this technology to open source QuantLib XVA pricing, and I'm going to demonstrate what type of performance we're able to achieve. I will then talk about where the performance is actually coming from. And in the end, we want to focus not only theoretical concepts, we also want to make it practical, and we pay attention to how to simplify development efforts and troubleshooting if someone needs to do that. Right, so don't hesitate to ask me additional questions during the talk. I'll try to keep the window open with the chat. Unfortunately, I don't see it at the moment. Chat, yeah, here. So I'm going to make a few stops on the way, and I'll address these questions. So what I want to see in the quant library. I want it to be simple. I want it to be simple to support, simple to develop, and easy to maintain. And what I mean by this, I know in the past people have been using templates in C++ as a way to speed up calculations, switching analytics to CUDA and making all more C-like and not object-oriented. This comes with pain, right? So you may do it once, but then you need to maintain it and develop further. It becomes very difficult. So I want to be able to implement my analytics in a simple fashion. So I'll call it humane C++. And when you have seen some error messages coming out of your C++ compiler with struggling to compile some of the template expressions you may see in real life, you understand what I mean. But at the same time, I don't want to sacrifice performance. I do want to see the best performance achievable. I wanted to be able to apply this to legacy stuff. I don't enjoy actually to come to my management and say, you know what, this time I want to rewrite my quant analytics from scratch. I want to be able to utilize what's already there. I know it's very good to start from scratch, but in practice, it's difficult to convince people to do that every 2 years. I want AAD to be a main citizen, first-class citizen of this approach. I do want to be able to differentiate functions as I go, and this should come very easy to me. Performance, of course. So where the performance can come these days. Multi-threading. Multi-threading is a big deal these days. Intel and other vendors, they're coming out with more and more CPU cores, and taking advantage of that requires multi-threading. And C++, it's a pain in C++ to do multi-threading. Yes, you can do so if you are a careful programmer, but again, if something does go wrong, troubleshooting that is difficult, and things do go wrong even at big houses, Facebook, Google. Time to time, things that do go wrong and need to troubleshoot them, and it's not something you would enjoy doing in financial library. Memory management. So this was C++ programmers were doing fighting for efficient memory management for ages now, right? And every time you think of a small objects, when you allocate them, you pay the penalty for allocation. And if you need to do that within your simulation, that means you pay this price on every iteration of your pricing simulation, for example. I want numerically stable vectorization. What I mean by this, modern CPUs, they come with vectorization support, similar to GPU can offer. And this vectorization is actually quite capable, but unfortunately in practice it's highly underutilized. And the reason for this is because if you rely on compiler to do automatic vectorization for you, you often end up with numerically unstable results, meaning you run your model once, you get one result, you run the model twice, you get something slightly different. And this is acceptable for gaming, but it's not necessarily acceptable for finance. And I wanted to have JIT. What is JIT? It's just-in-time compiler. I'm going to talk a little bit more about that, but it essentially allows you to utilize runtime information to run your code faster. And normally, when we compile C++, it's called ahead of execution compilation, and the compiler can only make such assumptions about the actual execution, the actual problem you're solving. It's not yet able to see this problem you're solving because you didn't provide all the details, such as specification of your simulation dates, traits, etc. All this information come in at runtime. And with JIT compiler, you can take advantage of knowing this information and building more optimal code. Optimal NUMA. Okay, this is something I learned about just recently. It's called non-uniform memory access, and it's actually very important to understand if you want to take advantage of all your CPU cores available. It's a little bit of advanced topic, but essentially you need to pay special attention on how you allocate memory to make the system work fast or in multi-core systems. So how it's all started. I was looking at various tools to do automatic differentiation, and I look at various open source and commercial tools that are out there. And I did see them utilizing very interesting pattern called operator overloading pattern. And I realized you can use this operator overloading pattern to extract valuation graph of your function, of your analytics, in fact, right? So if you do something like Monte Carlo simulation and you're essentially applying same calculations over and over again to just slightly different random numbers, okay, sometimes it's very different random numbers, why not use this valuation graph to do that? Why you execute sometimes inefficient code for code you implemented in C++? It may be efficient, maybe not, but you need to spend some time optimizing that to get it efficient. Why not use valuation graph to process full Monte Carlo samples? So what do I mean by operator overloading pattern? How it works? You start with your original function, and your function is a scalar double type it's using. So it's using, in this example, it takes two values, x and y, computes the result. And these values are using native double type in C++ compiler. You then change it to something that is a different type. And we call this active double. And for this type, we're able to change the behavior of operators. And in this example, we're going to replace the behavior of all the mathematical operations we want to capture, pretty much all of them. So multiplications, exponents, divisions, etc. So we do that, and this allows us to extract valuation graph. So how the valuation graph really contains all the primitive operations your analytics executes in order to go from random numbers from your interest rate curve, etc., to prices, to XVA numbers, all right? And you can track the full graph, full dependency coming from inputs to outputs. But what we're talking about today is AADC. It's actually a lot more than just AAD. And why is that? We have a wider application possible for our product. We can do what-if scenario analysis. And for what-if scenario analysis, you need to define your inputs, so interest rate curves, for example, and be able to shift them at certain bumps here and there, right? Normal AAD cannot do this. Normal AAD can only speed up your scenario risks at market data at T0. Similarly, we can do historical simulations, and we can speed that up as well, because we can reuse the same valuation graph and feed it with multiple historical samples. We do things like parameter fit, model parameter fitting, life risk systems. Here, what we mean by when we initialize this valuation graph and we know what it is, we can again feed it with new market data updates to process and calculate your positions and calculate life risk. What also turns out to be very interesting is that you can do parallel computing in such a simple fashion. It's unbelievable. With CUDA, you need to put a lot of effort into converting your existing C++ analytics into more or less plain C. You can use objects, etc., but you cannot use things like virtual functions there. So it's a limited support for all the features. But with this approach, you can keep your code object-oriented, and you can take advantage of all the features you like in C++ for convenience, and not pay the price for performance, and you get and take advantage of parallel computing. You can do things like mixing your C++ analytics and neural networks. And what do I mean by this? So if you have a process simulated in C++, and then you want to have some kind of function that you want to fit, and you want to approximate this function using neural networks, you can differentiate through the whole thing. You can differentiate through your payout, to cash flows, to neural network, to your scenario parameters, model parameters. And you can use things like reinforced learning to calibrate these small neural networks within your larger C++ analytics. This is a very powerful concept. You don't really need to go to Python to do your neural network training. You can do it on the fly inside C++. And classic AAD cannot really cope with this. It cannot help you with scenario analysis for sure. It can do AAD, but it will slow it down. So people don't really do training with classical operator overloading AAD in C++. And the reason for this is because it's slow. People tend to go to Python and TensorFlow to do training there. And we want to show that our solution is actually capable to compete, and in many cases delivers a much faster training performance than tools available in Python. So let's have an example. So what do we want to do? Let's look at a very simple example. We want to look at embarrassingly parallel problems. And I'm sure this kind of problems is very familiar to this audience. Let's say we have a set of Monte Carlo passes we need to price our portfolio on. So here we have MC randoms representing number of 10,000 Monte Carlo passes, and each Monte Carlo path is containing a vector of random numbers. We call generate randoms. Here we don't focus on the random number generator. This problem is well understood. That's not the main subject of this talk. And then we want to price our portfolio. And let's say we have this my complicated portfolio pricing function, which internally will do a lot of object-oriented stuff, right? So it will go somewhere deeper in the tree and object tree and use various pricing functions to do its job, right? So how do we speed up this kind of loop? What I want to do first is to change the double to IDouble, to active variable. We then define an object that we call pricing kernel, and this kernel will contain the evaluation graph we're recording. And in order to do the recording, we're going to record only one single Monte Carlo path. So we change 10,000 to 1. We then start the recording. We mark input vector as input to our graph. So we declare in advance what variables are inputs and what variables are outputs. And we simply call original analytics, right? But note that we only call it once, right? So yes, you do use original program, but you do it only for once and not for 10,000 simulations. So what happens when you stop recording? When you stop recording, you have yourself a machine code for this kernel built at runtime, and this kernel is capable of processing all the Monte Carlo samples in parallel, and it will do it in vector format, and it will do it in multi-threaded safe mode. At the same time, these kernels, they apply a lot of optimizations, so it turns out these kernels are much more potent than the original C++. Right. So how do I use it in practice? So when I have lots of old C++ laying around. Active variable. So our active variable is kind of different from anything you've seen before. Our active double is we call it IDouble, and I is for in place double. And it can be used simply as a drop-in replacement for double. I know you say that other active doubles also can be used as a drop-in replacements, but it's actually not true. Because once you use these active variables, you're kind of recording the tape already. So you need to have a tape. With this example, you can use the IDouble as a standalone type, doing the same work double would do, and not to record anything, not to use any graph logic, and not to use any AAD at this stage. So what we did for QuantLib. For QuantLib, they conveniently have a type def for real, and this by default it defaults to double value, and we've changed that. We changed this type def to point to IDouble, and we have a flag. We're able to compile QuantLib both ways with double and IDouble, and we recompiled QuantLib, and you know what? Turns out all unit tests pass, right? So you can actually change this type, recompile your existing analytics, and it would work as it was, albeit a little bit slower. I will touch on this later. Not significantly slower, but yes, there's going to be a little bit slowdown. But numerically, it will produce you the same results. So initial integration steps, at least, is very simple. So what would be another option for integration? And there are quite a few options out there. And some people say, let's template everything. So let's introduce this active type as a template for our analytics, similar to what you see on the picture. And let's do it everywhere in our C++ code. So the good thing about this, you can mix native and active mode at runtime. So you can get the best performance out of native execution, and when you need to switch from native to active and do your AAD or recording there. This is good. But now you have to change a lot of legacy code. Templatizing existing code may take quite a bit of effort to achieve, and quite a bit of years are spent on this. You need to reflect objects from native to active state. So when your system works in native state and you arrive to the point where you want to use AAD library, you then realize that you need to copy all your existing native objects into active state versions. And this is bad because now the beginning of recording of AAD, it's not cheap anymore, right? So you have to do some additional work in advance. Compilation time. Okay, and C++ is well known for very horrible compilation times, and this will just make it even worse because now all the implementations is moved to header files. So what would be typical program execution look like? How do we usually work? We load some data from databases or some files, and in this scenario, people would say, okay, let's use native types to do that, right? We then initialize market object, and here we can do some bootstrapping, some calibration of model parameters, etc. You can also use native types for that. But now you come to the point when you want to do simulation. And for simulation, that means you need to reflect and basically copy native market objects into their AAD market object versions. This is a little bit inconvenient, right? Because you need to at least maintain dependencies between these objects, etc. So with AADC, what you would do is to record one single Monte Carlo path using active type. That's all good. Then you simulate n paths very quickly using AADC, and this may include AAD if you like, and then you save results using native double type. Okay, so there is a little bit, some benefits of using templates, but note that you're trying to save time where the time isn't really that important. You don't really spend a lot of time loading data. At least numerical calculations. You don't do a lot of numerical calculations there. In market object creation and calibration, you do a little bit of calculations there, but it's hard to compare this to the actual simulation. So the actual simulation is taking the bulk of your execution time. So another way of doing the integration is just to do a type def. So type def is easier for integration, as I'm going to demonstrate. Record operations at any time, and this is unique to AADC. You can keep your program running and no tape exists, but your market objects are initialized, and at any given moment you can declare what your inputs are, outputs are, and do the recording for the evaluation graph. This is very convenient. You don't need to do this kind of reflection and creation of AAD versions of your market objects. You keep your code in CPP, so your development is reasonably fast. Active type, but there's a little price to pay for this. So your active type is now is used throughout your code, including loading data, initializing market objects, simulation, of course, and saving the results. So you do pay a little bit of performance penalty on loading data and market objects creation, but question is, how big is it? And it looks like it's not a very big problem. So a fair question would be, what do we do about if statements? I wonder why no one asked me already. If we're recording evaluation graph and we record this evaluation graph only once, what happens if for one Monte Carlo path, if statement takes a different branch, and how do we cope with this? What do we do about this? What we have at our disposal is active Boolean type. So we not only have active double type, but active Boolean type. And what it does, you can use normal Boolean expressions, and the result of these expressions would be active Boolean. So here, for the demonstration's sake, we have asset value, which is stochastic, so it will depend on your inputs. And we compare it to strike value, which is perhaps static value. But the result of this comparison is active Boolean. It may result in true or false at runtime, depending on the path and depending on the simulation Monte Carlo path would take. So this variable, the stochastic condition, represents a handle of this value that we will know later on. So what next? Really two approaches. One approach is very strict, right? So it gives you the compile time assurance that you will not have any problems. And what I mean by this, we forbid IBool to bool implicit conversion altogether. So you never can write an if statement with stochastic condition in it. And how do you deal with if statements if you have them in this situation? We introduce if function, and you use it in functional form. You simply provide 3 arguments. One argument is your stochastic condition, and second and third is true value and false value, very similar to what people do in Excel. Another approach is actually to allow IBool to bool conversion and just make your legacy code compile. It's very convenient because you don't need to do a lot of changes now. And believe me, in real code, there are a lot of if statements to cover if you didn't pay special attentions up front. But what do you do? Don't you lose execution branching? So what happens when your condition is 1 during the recording for the very first sample, and it will take another branching in the following execution for a different Monte Carlo path? So what happens here? So we separate 2 cases. We have stochastic and static if statements. And what do I mean by this? Let's look at all possible combinations of if statements we might have. If we have an if condition and it's outside of a recording graph, no problem, right? Because we're not recording anything. We're not going to repeat this if statement anymore. We just execute it here and move on, and we take the correct branch. What if condition is inside the recording, so it's somewhere within your pricing functions, but condition doesn't actually depend on kernel inputs. And this is actually a very, very common situation. And you may think of some dates logic. So you compare if a particular date is before or after a trade maturity, for example. And this condition isn't going to change depending on random numbers. It's going to stay the same all the time. So again, we don't need to do anything about this if condition. It can remain as is. So what if we have a condition which is stochastic? So this is the worst condition. So this condition may change depending on your random numbers, for example, or some other market inputs. In this case, we actually need to go and change that into functional form. And we need to introduce if to capture this. Again, we use the same syntax, 3 arguments, stochastic condition, which is IBool, and true value, false value, which are our active types to represent true and false value. So this is a little bit of work that needs to be put in to do that. But you may ask, how do I know if I need to use if somewhere deep in the code? And it's very understandable question, right? Because if you're dealing very large code base, you may not know that some if statements are actually stochastic conditions. And how do you locate those, and how do you convert those without going through all the lines one by one and not make change and not make errors anyway? So what we offer a tool for this. Basically, during the recording, when you traverse and create this evaluation graph, we can detect if some condition is actually stochastic, right? And if it is stochastic, we can record this point where this condition took place, and we can report this after recording. So it does happen at runtime, but typically you need to do it once to test a specific product type and address all the if statements within this product type, if there are any. Not always it's a problem. And you can after you're running that, you can identify this if statements semi-automatically, basically, this way, and convert them as needed. So to recap, we now can code in C++ and get best performance. And what do I mean by this? If you think of memory allocations in your C++ and you think how you use various STL objects, and you can potentially resize them and not resize them, etc. And if the questions about memory management is always on your mind, here it's not, because we execute original function only once. We do execute all this inefficient code once, but then we extract only evaluations that are needed from this user analytics, right? And we keep them in this graph ready for execution, and the graph itself can allocate all the memory it requires for execution up front. So, and this memory is linear, very well aligned, blah blah, very cache friendly. So this all memory allocations are eliminated. Things like virtual functions, these are actually performance killers. This is why people tend to prefer templates. These are also can be resolved only once during the one Monte Carlo sample, right? And once you have them resolved to specific objects, you extract these evaluations from these objects, and you form the graph, and you actually can inline virtual functions. This is something that normal compilers cannot do. Numerically stable AVX by design. So we never try to vectorize one sample of calculations. We always vectorize, we always compute 4 or 8 Monte Carlo samples at a time. So our calculations are independent from, like our past calculations are independent from each other. So you always get stable numerical results. And multi-threading. The evaluation graph, the beauty of it, its memory scope is limited. So we can allocate the memory needed to process this evaluation graph, and or we can run it in multi-thread without any issues and without any mutex locks. Right, so safe multi-threading. Reuse legacy code, yes. So as we showed it before, I'm going to do a live demo today. And you can take a very large projects and apply this technique and get results. Any questions so far? I guess no. I just move on. I don't have that much time. Right. So practical application to QuantLib and Open Risk Engine. It's about 650K total code lines. About 900 lines had to be changed. Mostly double-to-in conversions. Unit tests pass for QuantLib and for ORE. Examples work correctly. About 5 man work days to complete this. And now we're going to do a demo. So if you want to learn more about underlying products we've used in this demo, QuantLib is available here and ORE is available here. They have a very decent documentation for you to look at. Right. So as I promised, this is a demo for XVA engine. We're going to run a portfolio of 5 trades, and this is the original ORE built. So ORE is the XVA engine built on top of QuantLib. And in this example, what we do, we nicely read some market data from XML files, we initialize processes and start simulation. And here we take 5 instruments we need to price, 83 time steps for our time horizons, and 10,000 simulations we want to execute. We now go to look how AADC works in this situation. So it's basically the same code base with just a few changes and AADC integrated in it. But we're going to run the same example 3. And okay, what happens here? I need to scroll back. So what happens here? We also build the same size cube for XVA purposes. So it's 5 instruments, 83 time steps, and 10,000 simulations. We now record one Monte Carlo path. And in this example, we're only interested in acceleration. We don't do AAD. You can see the power of applying this just for accelerating your Monte Carlo or accelerating your scenario analysis, what-if analysis. It takes about 1.5 seconds to compile machine code, to compile this valuation graph into kernel that we can execute. The kernel size is 9.5 megabytes in memory. So this is amount of machine code instructions needed to capture this analytics. Reverse is not really used here. We don't do AAD in this example, but we can do AAD easily. Work size array is all the variables we require to do this analytics. This includes inputs, so our random numbers. This includes all the intermediate results, intermediate variables, and this includes outputs. Constant data is basically all the constants that some notionals, correlation data, etc., model calibrations. It's very similar to actual compiler. How it works. So what are the results? We running our random number generation. We do it ahead of the time. We generate all the random numbers needed for this simulation, and we spend 0.8 seconds doing that. We then execute full simulation using ADC kernels. So we're going to build this cube 583 by 10,000, but this time we can use multi-thread. In the original XVA engine, we couldn't do multi-threaded simulations, but here we can, because we know our kernels are thread safe. And it takes us about 0.7 seconds to do full simulation for 10,000 simulations. So you can see the timing it takes to do 10,000 simulation is actually faster than compilation. We're going to improve compilation in the future, I'm sure. But it shows how fast it is. So if you want to throw more Monte Carlo simulations here, you can do it at very little additional cost. And we're done. So we spent more time on writing the results, and the amount of results they write is quite significant. They save all the exposures, etc. So it takes a considerable amount of time in both cases. And if we go and look at the original ORE, it's still running. And it's going to run for, I'm not sure how long. But essentially, for this example, we obtain 150 times speed up for XVA calculations. And this is on one single, 150 times speed up on one single CPU core. In this demo, I do use 10 threads. So you need to multiply by 10 the timing, so it's going to be about 5 seconds actually to do full simulation using one CPU core and the ADC. And this ORE, it's a bit slow. So I'm going to stop it here, I guess, and move on. We don't have much time. Right. So this is the example 3. We got this acceleration. We've used AVX2, but AVX 512 is additionally, you can speed up things. Multi-threading is easier. So what I want to address now is like where the acceleration is coming from for this particular example. What I would say that object-oriented design is good, but it's not free. QuantLib is highly object-oriented, and there are a lot of abstractions take place. This is good for design, I guess. Some people prefer that, but for performance, it's not always ideal. So what we can do, ADC can take your object-oriented design and it can turn it into data-oriented design. So a design where you think how you calculate and process data. And thinking about data-oriented design is usually a lot more expensive. You need to put a lot more thought into designing systems like this, and it's hard to maintain them later on. But with AADC, it's easy. JIT compiled optimal code. I'm going to touch more on that. AVX actualization, inlining for virtual functions, better memory management, yeah, etc. So this is where, in this particular case, we get these tremendous results, right? So what is JIT optimal code? This is very, it's kind of new for finance, I guess, reasonably new. It was well known for web developing and scripting languages, where you turn less optimized code into more optimized code at runtime. And let's look at this example that you probably have seen in the Quant libraries many, many times. Linear interpolation. So what happens here, you take time t, and you want to interpolate within some buckets. And what you usually see is binary search to locate a specific bucket you need to calculate weights you apply on the left, weights apply on the right, and then do this linear interpolation. So what would be the equivalent of this function compiled in JIT at runtime when t is known and it's fixed? So we're looking at JIT version. So in fact, this function is going to depend on t, right? The t is gone, it's known. And if t is known, then lower bound is known. So we can simply replace the generic version of interpolation with this version, where we know which bucket we need to deal with. So we take just one value from y, another value from y, multiply it by two constants, add it together, and this is our result. And on top of this, we can do inlining of this in the pricing function. So you can see how big of a difference it can make. AAD tape. This is another point. So we know that AAD can consume significant amount of time, and a lot of work has been done into optimizing memory consumption in AAD. But I want to bring your attention to this example. So this is like a modified Fibonacci example. Here we initialize our variables v1 or v2. We want to use these variables as our inputs and compute sensitivities to these variables. And we made modification to the original formula. We use additional constants, C1 and C2. And as you can see, C1 and C2 are not stochastics. They are not input. We don't need sensitivities to these values. And within the loop, we calculate the next value V as a linear combination of V1 and V2. And classical AAD with tape, what it will do, it will record 4 elements on the tape, right? It will record C1 and C2, and it will record index of value V1 and V2 on the tape. And moving on to the next line, it will add another 4 elements for these 2 assignments. So overall, we're going to get for this loop, like we're going to continue running this loop. So we're going to save same results over and over again on the tape. We're going to get 80,000 elements on the tape just for this loop. So it doesn't really compress that well, to be honest. So how do we do it? When we compile this code in a graph, we can see that C1 and C2 are the same constants we use over and over again. So we're only going to record this C1 and C2 once. We generate machine code to represent this relation graph, and the machine code is structured in such a way that it will basically reference the same values, V1 and V2, going through this loop. So it's going to be very compressible, 100 times or more in this situation. So in a nutshell, for linear problems, when you do this kind of repetitive calculations, ADC memory footprint is very similar to the original algorithm, but classic AAD will grow with the number of operations. So I would say this is a tape compression on a different level, really. Right. So it's all good, but what if things don't work well? Like, how do we make it practical? And we have developed an approach that you can utilize to find any problems. And usually that means you just locate Monte Carlo path to analyze and compare the recording with your original implementation. You can add additional printing, so you can introduce this statement where you wrap your variable, and this wrapper can print out not only the values computed for forward execution, but also can print out adjoints for X for additional troubleshooting. So what do you do with these adjoints? You first want to make sure that the code is producing correct results for your original Scalar code and for the recording, for the values, not for the joins. So once you are sure that the values for all Monte Carlo passes are aligned, what if there are problems with adjoints? And this is a very neat trick that we have. What you can do, you have this kind of evaluation graph. You have inputs on the left, results on the right, and some variable in the middle. So what we can do, we can record this graph, but later on we can add additional perturbation to this intermediate value at our will, externally. So we have this recorded function available to us, and then when we execute this forward function, we can bump intermediate value back and forth in order to calculate first derivative or second derivative, whatever we prefer, using finite difference. And we can compare the finite difference result with a joint result and automatically break on a specific variable for which adjoints start to diverge. And this is a very powerful tool because, again, if you have a big quant library, which you basically can view it as a black box, and you don't know where things go wrong, you can simply use this pattern and identify where in the source code exactly things begin to break. Well, it's not stopped here, it's just introduction to ADC. We have active development in covering American Monte Carlo projects, machine learning and neural networks for quant models. Scripting language integration is also something that we definitely can take advantage of this in this situation. You can have generic capability for scripting language for your various payoffs. At the same time, you can convert them at runtime in something that you can run very efficiently. We have Python integration, and this is it. Yeah, so this is ADC project. This is basically what we offer. We're looking for POC projects to do, and we have demo licenses available, academic licenses available. And I guess I have 5 minutes left for questions. Okay, unless someone wants me to talk about something else, I can use this time, or...
Looks like everybody might have had all their questions answered. So thank you very much, Dmitri.
Okay.
Obviously, everyone's now got 8 minutes to have a coffee or whatever you need to do. So thank you.
Sounds good. Thank you.